So as was just mentioned, I'm Siddharth. I'm from the Indian Institute of Science, and for the next 10 odd lectures, we'll be discussing fair division. So the title itself is quite suggestive of what this topic deals with, but let's just start with a working description of what this active area of research entails. So the idea here is that this is essentially a study of fairly allocating resources among a bunch of people, among a bunch of participants that have equal entitlements but distinct preferences. So we will, like in due course, see sort of the limitations of this description, but it's good to pin down one working definition. So it'll sort of serve as a useful guide to at least get us started and get a handle of what this topic is about, what this stream of work is about. So before we actually sort of jump in, let me highlight two specific aspects of this description. The first one is that this is actually a formal study. It's a mathematical study. In particular, like even the definition of fairness is not obvious to begin with. Like how do you, like you have a generic sense of what is fair and what is not, but here we are actually our focus is on provable guarantees. So right from the onset, we'll actually try to like pin down rigorous mathematical definitions of what is fair, what is not fair, and then try to work within these sort of well-defined constructs. So sort of that's a very important point, and that should have been sort of impressed upon you even in other topics of algorithmic game theory that you have kind of seen in the past few days. So what I would like to say is that this is sort of something that one must appreciate is that sort of mathematical rigor here should not be considered as a liability. It's not an afterthought. It's not something that you're doing just for the sake of doing it. To begin with, like if I ask you for a definition of fairness, that in itself is a non-trivial task. So right from the onset, like a mathematical treatment is warranted. I would also like to impress upon the fact, and this will be clear through many examples, that in many cases, this is actually the mathematical analysis goes hand in hand with the design aspect of things. We'll actually see results that are certainly a priori not obvious in the sense that, so here's a specific example, and this will certainly become clear by the end of today. There's a notion of fairness called NB freeness. I haven't defined it, but it sort of has a, I mean, it means what it's supposed to mean, that you somehow divide a resource, divide things such that no one is envious of other participants in the fair division exercise. And it will be a priori completely not obvious whether such a fair division exists. It will require sort of deep and beautiful mathematical connections to actually prove that such a thing exists. So here, math is not sort of something that you do post facto. It's very important. It's important even to know if something fair exists or not. This also is true for the algorithmic aspects of what we'll study, in the sense that it's typically not the case that you have an algorithm that you somehow know is correct, and you then just try to, for legal reasons, prove that it's correct. Many a times, the mathematical analysis helps you design the algorithm. So it's a meta observation here, but I would like you to keep this at the back of your mind as we actually go through this entire exercise, as we sort of go through a bunch of theorem proofs. I mean, you should see it as something that's actually developing the theory rather than like a rigid framework that has been forced upon you. So appreciate the math that sort of goes into it, not just for the fact that it lets you prove things, but in fact for the reason that it will let you develop things, design algorithms. So that's sort of that's one aspect of what we are going to do. The other important point that I would like to highlight is in this sort of definition or this description of fair division is that what makes this problem interesting is the fact that the preferences here are distinct. The agents that are participating in a fair division exercise that are trying to get part or parts of a resource value things differently. They have different choices, and this is what makes, in effect, make the whole exercise non-trivial. Like if the preferences of everyone was completely aligned, in almost all cases the sort of problem of fair division would become much simpler. So that's an important aspect. I've written equal entitlements just to get us started. Of course, there are extensions where you have participants who have different entitlements. Someone is sort of deemed to get more of the resource than others, but as I said, like rather than trying to pinpoint weaknesses of this working definition, let's start with it and see where it sort of takes us. At least it's a useful guide for the first few lectures, and sort of will kind of try to refine or polish this description, polish this working definition as we go along. So that's sort of the focus. It's focus on rigor, focus on mathematical guarantees, and obviously, given the fact that the background of the presenter is from it comes from computer science, our perspective will be computational. So by this I mean that we'll focus a lot on algorithms, we'll focus a lot on talking about complexity or how do I find things, so on and so forth. This is sort of an obvious statement. We will look at things from an algorithmic lens. What is sort of non-obvious from a computational perspective is the fact that this also brings along with it a sort of flavor of approximation. So there is again, like fair division is literally a classic topic in microeconomics. In fact, the first reference I'll give you is going to be the Bible. So if you like chronologically, good luck trying to beat this in terms of prior work. But the point though is that while there has been a lot of work in microeconomics on fair division, we will sort of look at it from the computational side of things. This, as I said, would sort of imply that we'll focus on algorithms more on and less on things like an axiomatic treatment. In microeconomics, fair division is also studied in the sort of context of markets. Like if you know what Arrow-Debreu markets are, then this is sort of another framework for talking about fair division. We will very briefly sort of allude to that perspective, that vantage point. We'll throughout try to sort of look at algorithms and try to even prove existential results whenever possible through the means of algorithms. The second point though is actually the point about approximations is sort of is not as obvious. Economics, microeconomics has vastly, I mean this is, of course there are exceptions, but predominantly focused on exact results. And a very important intellectual sort of export of computer science in algorithmic theory, algorithmic game theory is in fact looking at approximation guarantees. So this not only lets us ask sort of new questions, but it allows us to extend results. And in the next lecture or so, we'll actually see that there are impossibility results which you can circumvent by looking at approximations. So this again is sort of something that it's useful for you to keep at the back of your mind. The fact that looking at approximations actually changes the landscape. It lets us plant fertile questions in seemingly barren land. So that's also something that there's a very sort of a common theme in theoretical computer science and sort of complements the work in game theory, complements the classical work in fair division a lot. So all of these are meta points. I just wanted to state them upfront so that you have them with you, and when I actually get to specific examples, I will point it again. But yeah, it's actually good to appreciate when you're studying a subject, so what's the advantage and disadvantage of sort of coming from a particular perspective, and this sort of, again, it's a good thing for us to sort of appreciate as we sort of go along. Right. So that's a very broad definition. If there are no questions, I'll actually jump right in with a very sort of concrete protocol, with a very sort of concrete example to sort of get us started towards fair division. So this is probably a good time to ask a question about the meta goals that we are trying to achieve here. Okay, so let's get started, and let me actually look at an algorithm. Let me actually sort of look at a protocol that I said in fact appears quite some time ago. This is called the cut and choose protocol. So I would actually like to dive deep, solve one specific problem, and then probably towards the end of the lecture we'll sort of step back and set up our roadmap. I just didn't want to throw a bunch of jargon at you and say, okay, we'll do this, we'll cover that. We'll do this contents of this lecture series later, but let's actually get our feet wet and solve one very specific and classic problem before we actually try to sort of see what's our roadmap, try to sort of develop a taxonomy for fair division. So, I mean, as the name suggests, it's a protocol for dividing something. It's also called divide and choose, or also referred to as I cut you choose. And this in fact appears in an epic Greek poem of Theogony, which, I mean, okay, if in terms of high standards, this was an epic Greek poem of written in the sort of 8th century BC, and it's about the genealogy of Greek gods. So this is, yeah, starting with a very high bar in terms of content, and there this sort of protocol was actually executed between Prometheus and Zeus. This protocol also makes an appearance in the Bible, the book of Genesis. It's a protocol that was executed between two parties, so two participating agents, two agents who want to share something fairly, which were Abraham and Lot. So this is Bible, book of Genesis, and what Abraham and Lot wanted to do was divide a piece of land, it's called the land of Canaan, fairly between themselves. So the agents, the players or the participating bodies in this fair division exercise are just two people, Abraham and Lot. The resource at hand is a piece of land, so it's just a chunk of land. And the way they do it, the setting that's sort of described in the Bible is that, so let's say this is the piece of land. So it's a two-step process. So what ended up happening was So what Abraham did was looked at the land and said, okay, here's a border, here's a left part of it, and here's a right part of it. And Abraham divided it such that he was indifferent between these two pieces. Right. So for Abraham, this sort of line actually gave rise to two parts. The part on the left was of the same value to Abraham as the part to the right. Let me stop here and emphasize two sort of important aspects of this exercise. The first is that the resource at hand, which is land, is actually divisible. Right. So it's meaningful for me to say half, you get half, I get half, I get 1/3, you get 2/3, I get 1/4, you get 3/4. So this is a resource that can be divided fractionally, that can be shared fractionally among two or more parties. Note that this is certainly not the case in general. Like, this is not a universal feature. I can have resources that cannot be shared integrally. So for example, say I'm looking at seats in a summer school, like the opportunity to attend a summer school, and I would certainly like to divide it fairly among students of many universities. So these allocation, these seats, the right to attend, say, this summer school is not essentially, okay, it's not really a divisible resource. I can't say, okay, you know what, 1/3 of the time you'll attend and that's it, I'll kick you out. 2/3 of the time is some other student that will come in and I'll sort of do some time sharing with preemption. So that's a bad idea. Okay, there are other resources and we'll get to them. Those are called indivisible or discrete resources. But the one at hand here, like land, or a sweeter example is a cake, which are things that can be fractionally assigned. This is certainly the case here. The second important property of the resource is that it is heterogeneous. Not all parts of the resource are sort of same value to either of the two players. There could be parts of the land that are more fertile, the parts of the land that have more minerals, they can have hills, so on and so forth, more water accessibility. So the good is not uniformly, this resource is not uniformly valued, it's heterogeneous in that sense. Okay, so that's the sort of preface about the resource at hand. Let's get back to our protocol. So what did Abraham do? Okay, he sort of divided this land by say a vertical line, a border, into a left part and a right part that, according to Abraham, according to him, was of equal value. And then the next step is quite natural. He asked Lot, the other participant in this exercise, to choose one of these parts. Like go ahead, and here are the two pieces, and said, okay, pick one. Okay, so very simple protocol. I mean, clean enough to have made an appearance in the Bible, in 8th century, sort of 8th century BC Greek poem. Of course, this is sort of something very natural that people have thought about in different eras and sort of different civilizations. And my claim to you, which is sort of somewhat informal right now, is that this will lead to a division. This will lead to a sort of partition of the resource, this piece of land, in a fair manner. Right. So before I actually go on and sort of prescribe what fairness gets achieved, let me ask you, why do you think this is a fair way to divide land between two people? So, any ideas? Yeah, so I actually want to tease out the fact that the notion of fairness isn't obvious. I mean, you might look back and say, yeah, look, I mean, I divided and you get to choose, so it's fair. I want to actually see, yeah, like before I actually get to the definition, which on its face will look, okay, obviously this is how you should have defined things. It's important to sort of appreciate the fact that the definition in itself is an important non-trivial mathematical contribution of what we are going to look at. In particular, a lot of algorithmic game theory, the solution concept itself is something of value. This is not something that's like obvious that's there. So yeah, it's kind of take a minute here to sort of try to see if we can in some rigorous sense say that this is fair. Sort of a unfair question on my part because I haven't given you any formal model. This is more of a teaser of sorts. So in the sense that say you have a cake and the two children, like if you were to actually run this exercise between them, well, yeah, children typically aren't happy, but this is as good as you can be. Like you can ask one of the first child to divide the cake and the other guy gets to pick. Chances are, among other things, this is going to satisfy both of them. But let's try to actually sort of see what this means. And in particular, what I want to say, like the first aspect that sort of needs attention here is that, so it's fair in the following sense, that so Abraham and Lot are my two participating agents, and my sort of informal claim right now is that neither of them is actually envious of the other person's piece. And again, we will very soon sort of pin down a rigorous model and try to like write a mathematical equation of what this means. But the idea here is that, look, I mean, if Abraham were to actually divide the piece of land into two parts that he equally valued, then he would be indifferent between the two. He actually got to pick a boundary. He actually sort of got to pick a border between these two pieces such that, okay, he said both of them are equally good for him, both of them have the same value for Abraham. So in the sense that doesn't matter what Lot chose, Abraham was happy. He wouldn't say, okay, look, you know what, I should have done this, but okay, then you should have divided it equally. And at the same time, Lot is also not envious of Abraham because he got to pick first. He looked at the two pieces, picked the one that he valued more. Right, so in that sense, at the end of it, neither one of them is envious. Said in a different manner, neither one of them would actually want to trade their own piece with the other one. Right, so it's sort of a fair division in that sense. It's fair in the sense that it satisfies everyone. It's also fair in the sense that with some assumptions on the value, their preferences, you can argue that both of them actually get half of their total value for the land. Again, I am trying to sort of systematically move towards a rigorous model, so I haven't given you any mathematical definition. But again, this is sort of an informal claim which I hope you can appreciate, that look, Abraham actually divided it such that the value of the two were equal, so both of them were value half of the total value. So of course, irrespective of Lot's choice, Abraham got half, and Lot is in some sense in a better position well, he gets to choose the higher valued piece, so which is going to be again at least half of the total value, right? So very slyly I have made an assumption about the valuation. Can someone point that out for me? Yes. Right. Right. Perfect. And at the same time, can you point out why I get this half here? So I'm saying that the value that say Abraham gets is half of his total value for the entire piece of land, and at the same time the piece that Lot gets is half of the Lot's value for the entire piece of land. What assumption have I made here? The land is heterogeneous. Okay, maybe I'm jumping ahead, but in some sense I'm saying the values are additive. Right? Your value somehow, it's not the case that if you get the whole land only then you get a value out of it. It's if you get, so there is a point where you sort of can divide and the values can be half. So this is sort of additivity. Again, I'm trying to sort of jump ahead, but there are sort of subtle assumptions I've made, but let's just assume that the values of the two participants, both Abraham and Lot, are well behaved in a natural sense. Then again, you will have these two guarantees. And again, thanks for your patience, because very soon you'll actually see equations for this, and you'll only see equations for this after that. So it's at least half, right? For Abraham, like if he follows the protocol, it will be exactly half. For Lot, it will be at least half. Yes. So, okay, that's enough of a story time. So let's steadily move towards a formal framework and try to express this observation in a sort of in mathematical sense. So it's going to be slightly oxymoronic. I'm going to tell you here's a formal framework, and the formal framework is called cake cutting. So the word cake here again is sort of, as I said, it's a sweet analogy for a heterogeneous divisible resource. And right now we have done this for two agents, so let's kind of stick to it. The way this heterogeneous divisible resource is modeled is sort of the so I'm again following standard sort of following standard framework. This divisible resource is modeled as a line segment. It's just the segment between 0 and 1, and the partition, say between two agents, will just correspond to a point where I exactly cut this line segment. The left part, the left interval, will be assigned to one of the two agents, and the right part will be assigned to one of the two agents. So the idea here is that here's my land, here's my cake, here's my divisible resource. What Abraham does is actually picks a point here and let's call it x. So it's just some point. So now I have two disjoint intervals that partition this resource. So the point x is marked by Abraham, and then Lot gets to choose between one of these two intervals. So the Lot can choose the interval 0x or x1. So I'm not going to like really pay attention to the boundary intersection, in particular just for the time being I've written it as an interval that's open at x, but again with slight abuse of notation I'll just consider it intervals like this and assume that this boundary point is just a boundary point. I'll still call these two intervals as non-intersecting, I'll still call these intervals as disjoint. So if you really want to be rigorous about it, the intervals are open, but again so it's just a sort of, I can impose a convention and just argue that look, this is the boundary points are sort of, I'll call intervals disjoint if they either completely non-intersect or the intersection is just a boundary point. Right? We'll make an assumption about the value, the preferences of the participating agents that will sort of make it even more precise, but for the time being, yeah, this is sort of the convention. So I have two intervals and they are disjoint. And again, the exercise is this point x is marked by Abraham. These intervals are prescribed by Abraham, and Lot now gets to choose one of them, and the sort of process goes on. So a feature that will sort of keep reoccurring, and let me digress and point it out right now, is that I really don't need an arbitration in this process. Note that I did not need a third party, I did not need an intervention of the government or someone else to actually end up at this fair division. Abraham and Lot actually managed to execute this protocol, execute this algorithm just between themselves. There's no arbitration, there's no moderation required. And the second key aspect of this model, this framework, is that the preferences of the agents are expressed as valuation functions. So a fairly important modeling aspect. There is certainly a lot of work in the sort of complementary side of things where the preferences are ordinal. So for example, you have seen stable matching setup, right? In that setup, you didn't have numerical values, you didn't have a function that assigned numbers for preferences, you just had a ordering. You had preferences of the sort that, do you like this option better than this option? Do you like this piece more than this piece? In contrast, prominently and sort of most of the work that's been done in fair division in computer science, again, there are exceptions, but predominantly in computer science, the treatment is cardinal, as in you work with valuation functions, you work with numerical values, and this is what will conform to here as well. That is, we'll say that the preferences, the choices of the agents participating in a fair division exercise will be expressed numerically, as in, you look at an option, you look at a piece, you look at an interval in the segment, and the higher the value, the more preferred it is by that specific agent. So in particular, what you have here is that, so you have two agents here, Abraham and Lot. Let's say I look at either of these two agents, let me call it I. So I can be either Abraham or one of the two, but for both I actually have a function v of I, and what this function does is that it assigns a value, say a non-negative value. So for every interval in my line segment. So this is sort of a function, say, that's specified, and what it says is that, okay, I look at my segment, I pick any interval I, so this is I, it starts at say x, ends at y, and for both agents there will be a value to it, right? And the higher the value, the sort of more preferred it is by the agent. So the standard interpretation, the standard sort of convention is being followed here. Again, let me emphasize that almost through the entirety of our discussion on fair division, we will not talk about ordinal preferences, preferences where agents don't have numerical values, they only have like orderings, they only have choices of this is better, that's not. We'll not deal with it, we'll deal with valuations, we'll deal with settings where one way or the other, there are numerical values associated with what you get. In this particular current context, this means that if I give you an interval, both Abraham and Lot have a numerical value associated with it, right? It says, okay, I look at this interval, this is of value 0.3 to me. I look at another interval, that's of value 0.5 to Abraham, value 0.6 to Lot. And going back, when I say that the preferences are distinct, again, just jumping back to the definition, this distinct preferences essentially means that these valuation functions are different. Right? Different Abraham and Lot don't have the identical valuation function. Okay, so this is nothing but the value right. So for every interval there is a value, and this is sort of the value that this this sort of agent has for this interval. They can be different for Abraham and Lot, and we'll very soon sort of consider natural assumptions, and in some sense for particular, some of them will be actually necessary assumptions on these valuation functions. But for the time being, let's assume that these valuations are well behaved, right? What does well behaved mean? Well, it means what it means. Again, I'll sort of formalize it, but right, I'll actually would want to like state something before we actually get into the nitty-gritties of what these properties are. But note that if I look at the cut and choose protocol, what Abraham, which is our first agent, can say divide the cake, land, what have you, the segment, in two pieces of equal value. So as was the picture before, I have this, Abraham marks a cut such that if I look at so Abraham is agent 1, that's just an arbitrary index. So the subscript here again denotes it's the identity of the agent. So V subscript 1 means the value of Abraham. So he picks a point x such that the following equality holds, which means that for Abraham, he's indifferent between the left interval, the interval between 0 and x, and the right interval, the interval between x and 1. Right. So that's the sort of onus on Abraham. So he does this partitioning, and now Lot, which is agent 2, selects so he kind of says and does something that's in Lot's best interest, pick the one of the two which is of higher value to Lot. So again, say for example, so the subscript here again denotes the identity of the agent. So I'm looking at the value of the second agent, looking at the value of lot. So say that this is actually strictly better than this. So okay, so far so good. I mean, yeah, if you think I'm going slowly, wait for it, I'll speed up. Nonetheless, what this means is that, note, I've invoked these value functions only for intervals, and with this in mind, I can now state what the two properties, the two senses in which the things are fair. So again, the rule of thumb, the convention that will always follow is that the subscript always denotes the identity of the agent. This is true for, say, the valuation functions. So this is valuation of the second agent, this is valuation of the first agent, and will also follow the same convention when it comes to intervals. So in particular, with this example, with this specific scenario in mind, lot ends up picking the left interval. So I'll call this left interval as I2, the subscript 2 denoting that this interval goes to the second agent, and I1 as the interval that gets assigned to the first agent, the interval that Abraham is left with. Is that clear? It's just an indexing rule I'll follow. It's nothing but a notational convention. Okay. So what does this mean? This means that so if I look at the value that the first agent has for the interval it has obtained. So V1 is the value of the first agent, I1 is the right interval, the interval that agent 1 ends up being, then this is actually, I'm being sort of redundant here. This is actually an equality. It's an equality because x was selected precisely to make these two values equal, make the two intervals of equal value. But of course, I can write it as that the value that agent 1 has for the interval that's assigned to it is at least the value that agent 1 has for the other interval. Okay. So what can I write on the right hand side here? And the subscripts do matter, so can someone fill this in for me? What is that? V, perfect. So V2, the value that 2 has for I1. All right, so let's parse through this because it's an important definition that will generalize very quickly. This says that, again, this is exactly what I meant when I wrote earlier that the division is going to be NV free. Let me bring that up. Yeah, so this is exactly this line written in an equation form. It means that both the agents do not envy the other person. In particular, this means that agent 1, guided by its own valuation function, its own preference, looks at its own piece and says, you know what, I like I1 better than, or at least as much as I2. So I'll certainly not envy you, I'll certainly not trade with the second agent. And simultaneously, the second agent looks at the interval that's been assigned to it, V2 of I2, and says, you know what, I'm actually happier with what I got. In fact, I got to select it. So the value that agent 2 has for its own interval is at least as much as the value that it has for the first interval. Okay, perfect. So that's what it means to be NV free, again, in the two agent case. Note that I1 and I2 can be switched, nothing will change. Lot could have picked the right interval x to 1, and I would have just indexed it as I1, and like exactly the same equation would have held. Nothing would have changed. It's just re-indexing or naming things differently. So that's the first property. Furthermore, I want to argue that what you have here is that if I look at these two equations, right, and I sum it up for, say, so I want to claim that again, if I look at the value that agent 1 has for the interval that it receives, the interval I1, then this is at least half of the value that agent 1 has for the whole resource for the entire cake, right? So cake cutting is a formal term, and we will take it seriously, and whenever I say cake cutting, I actually mean this very important mathematical problem. So yeah, so again, I'll try to get to it and I'll prove this more generally, but this is fair in the sense that the agent is getting a proportional share. The value of half here is that there are two agents. They're saying there are two agents and both of them actually end up getting at least half of their total value. So it's fair in this proportional sense as well. So this also holds for second agent, that if the second agent looks at the value it has for the entire cake, which is the right hand side, the piece that it gets is at least half of the two. Okay, again, having not specified the properties of the valuations and like guiding you with on a sort of a thin rope saying that these valuations are well behaved, which one do you think is a stronger property for the case of two agents? Like which one actually implies the other, do you think? Again, I'm kind of jumping ahead. I haven't specified the properties of the valuations, but just trying to see what the intuitive grasp is. So what is that? The first one. Okay. Can we have a vote on this? Again, it's not a fair question. I haven't given you the properties of the valuations, but first one, second one. Is there a third option? Maybe there is. Okay, for the case of two agents, these two are equivalent. Again, not having specified all the properties, but we'll see this that when you have two agents, NV freeness, i.e. the first set of equations are equivalent to proportionality, i.e. the second pair of equations. But the sort of paradise is lost exactly when you at two agents. When you go beyond two agents, these two sort of solution concepts, these two notions of fairness diverge, and they diverge in some drastic senses. Sort of almost the entirety of today will be sort of spent sort of explaining to you or trying to impress upon the fact that one, proportionality is a much tamer solution concept. It's a much more tractable solution concept than the other one. Let me also sort of make one quick note before I move on to finally tell you the details, the nitty-gritty details of this cake cutting model. Is the fact that note that not only have I given you an algorithm to find a proportional cake division, i.e. a division that satisfies this second set of properties, and not only have I given you an algorithm that's able to find an NV-free cake division, i.e. a cake division that satisfies these first two set of properties. What I have done is also prove that such things always exist. right? So it's not just an algorithmic result, it's an existential result. I am saying that if you define fairness in one of these two manners, that at least for two agents, I know that not only, I mean, of course, the fact that you can always find them means that these things always exist. Right, so it's a very important point. It's an existential result as well. I'm saying this is like Sanjeevani, it's somewhere there, and not just that, you're capable enough to find it. So this is sort of a constructive proof of existence, sort of a very nice property to have, and we'll see results. In particular, we'll see results for NV freeness with many more agents, where this is sort of a elusive goal, where it's not obvious till now to the entire research community whether even good approximations of NV freeness exist. Well, they exist, but whether they can be computed efficiently. So in the guise of an algorithm, I have actually also proved that such a fair division in both these senses of fairness always exists. Okay, so having been informal for quite some time, let me actually sort of get to the model. And again, as I said, the cake here is the line segment 0, 1. It's this interval, it's divisible, so you can sort of cut at any point of time. It's heterogeneous in the sense that you have these So now I'm looking at a general case of n agents. So far we have been looking at the very special case of 2 agents, but now, I mean, you can have a divisible resource, you just don't have 2 people, you have many people, say you have n players, n participants, n agents. And again, you have valuation functions. So again, I'm assuming here that the valuations are non-negative. So this is the value that sort of agent I has for any interval. A. Right, so again, you have done it for 2 agents, you have more agents, you can also sort of look at a more general problem. And so that's the setup. These sort of assumptions the first one, which I've already alluded to here, is that the valuations are non-negative. Right, so Vi of I is equal to for all I. So this is genuinely a cake, right? You will not be sorry for having received it. This is certainly by no means a universal phenomena. A very sort of interesting open question is whether existence result hold when these are negative for certain parts, and sort of creatively that's called the burnt cake problem. When we get to sort of open problems, I will sort of detail this a bit more, but this is sort of an assumption which is sort of important to us. Think of it as dividing a good versus dividing a chore, right? So in the chore case, you have negative values. This is something that we'll sort of address later on. But for the time being, this is an assumption that we are going to make, that the values are non-negative. It can be 0. There can be part of the cake that you really don't like. It will not be okay, fine. Or you don't eat it, you pass it along to me, and that's it. So you don't have negative value for the cake. You're not that calorie conscious. At least I'm not. The second property, the second assumption that we'll make here is that that the valuations are divisible. what does this formally mean? It means that so what I'm writing here is the definition of divisibility. It's a property that I am going to assume on the valuation functions. All the results I'm going to subsequently talk about will work within these assumptions, will work when the valuations satisfy these three assumptions, two of which are written now. So the fact the valuations are divisible means that for every interval, so let's say, so I take any interval xy and any parameter lambda, so what it says is that, okay, I have some interval xy, this is my interval, and now you give me any scaling parameter lambda, there is going to be a cut, there's going to be a z that's between x and y, such that, and this is sort of for all agents, if agent I looks at this subinterval x to z, then this is of value lambda times agent i's value for the whole interval I. Right. So this in particular means that Abraham can look at, instantiate it for I as 0, 1, the whole resource, the whole cake, and find a point z such that the value is exactly half of the total, the value to the left is exactly half of the total value, right. I want it more generally, in particular I want it for all intervals and for all possible lambdas. So pick a lambda, 1/3, 2/3, 0.6, 0.3, pick any interval I. What this says is that you can actually cut it such that the value here, this subinterval, is of value lambda times the sort of value that I has for the entire interval I. Is this clear? Okay, so this, unlike the first property of non-negativity, is an unavoidable assumption. In particular, what this assumption does is it rules out point masses. Right? It rules the fact out that your value is completely concentrated on a single point in the interval. And someone explain to me why that is the case. So this implies that VI's, the valuation for any agent I, is non-atomic. When I say non-atomic, I mean it's the case that there isn't a single point C where your value completely lies. So when you look at the cake, it's not that there's a specific point and you say, okay, if I get this, I get value. If I don't get it, everything is lost. Why is this? Why does this property, why does this assumption rule this case out? Right. Exactly. Yeah. So it's a perfect example. There's a diamond sitting right in the middle of the cake. Certainly won't want to eat it, but or maybe you do. But there's no way to divide it in the sense that if I look at that diamond, if I give you that point and then I say give me something that's value half of it, you can't break it. So the property gets violated. This means that the valuations are non-atomic. Let me ask another follow-up question. Say if the valuation is atomic, right? Then why does the protocol, or even for two agents, why am I in trouble? Why is it the case that say I can't find NV free or proportional division. No? So let's just circle back and say this was the case. Like if there was a specific point in the entire land where there was a diamond, and Abraham's value was just completely concentrated on this diamond, right? And the diamond cannot be divided, cannot be partitioned. Can Abraham then find a point where the value is half and half? Can the first step of the protocol be executed? No, right. So hence, if I have an atomic valuation, if I have the case that the thing is completely concentrated, I am in trouble. The sort of guarantees that I've made informally won't work. So in that sense, this is sort of a crucial assumption. It's an assumption that that's forced upon us. Okay, so that's the second assumption. The third one that I'll make is that the valuations, all the valuations are additive. And this simply means that yeah, there would be no protocol. Exactly, yeah, it's a good point. Like it's not just that the suggested protocol would fail. Like there's no way to then divide it into two parts. Like both of the participants, say even in the case of, so here we have like general n agents, but even if I have only two agents, there's a point mass. Both of them only value this, so it's nothing will happen. Like either the first guy will get it or the second guy. There's certainly not going to be proportional or NV free. So point masses are a no-no in this case, and so divisibility is sort of in that sense required. Right. So again, this is, second one is sort of essential. The first one can be relaxed. There's some results for like cake division with negative values, burnt cake as it's called. The third one also is something that we'll discuss in the open problem section, whether additivity is an essential requirement or not. But for the time being, this is sort of a natural assumption. It's a standard assumption in this line of work. So we'll sort of, at least for the initial part of things, we'll sort of follow it along. And what this says is that the definition of additivity is quite natural. This says that you pick any two disjoint intervals, I and I prime, and for any agent I, if you look at the value of this union, so this is, note that this union is not necessarily a sort of a single connected piece. This is two crumbs of the cake, two disconnected intervals. But now you can talk about the value that you have, agent I has for this union. This is nothing, again, this is disjoint. It's just the sum of the values. So if you partition it among n pieces, your total sort of values is the sum of these things. What this lets us do is it enables us to extend the valuation function to finite union of intervals. So that's the formal framework. That's the sort of rules of the interactions that we'll sort of work with. And these finite unions are typically called pieces of the cake or crumbs, so on and so forth. But these are the three assumptions that I'm going to make. And something that sort of follows without loss of generality is normalization. So I'll assume, and again, this is just a scaling exercise. There's nothing, it's not nothing essential about it, that for every agent, the value for this entire resource, for this entire cake is scaled at 1. So So every agent looks at the whole cake, the whole segment. The value is just equal to 1. This is normalization. If it's 10, you just divide everything by 10 and you sort of get that. This is sort of nothing profound here. Okay, so 3 assumptions and 1 sort of a normalization property that we can assume. Now with this in hand, if there are questions, I can answer them now, or like move on to like circle back to the two notions that we have seen, NV freeness and proportionality, and actually define it more generally. More generally in the sense for like n agents now. Right, so this is sort of teething pains. You'll have to, like, if I want to talk about any formal result, you will have to sort of bear with me for some definitions and basic modeling things. I sort of assure you that interesting ideas will come soon. So far, this is just sort of grunt work in the sense of building towards a common language to talk about this cake cutting problem, like a framework where we can sort of develop ideas and sort of share interesting algorithms and results. But yeah, so it's just so far so good, the kind of the sort of minimal baggage that you have to carry along to talk about these results. And as I said, I'll not be explicit about it, but if all the results that we will sort of discuss in the cake cutting context will be under the assumption that these 3 properties hold for the valuation functions. Yeah, again, just be patient and I'll stop with the definitions. But yeah, it's good to have, again, rigor is important. Let's have all the definitions out of the way to like get to nice, interesting results. So first thing, again, this is sort of a repetition, and so I'll define an allocation of as just as an n partition of 0, 1. So n as in there are n agents. I look at my cake, I look at my divisible resource and divide it into disjoint intervals whose union covers the entire cake. So it's a partition of the cake where again the indexing is as before. So interval II is assigned to agent I. So the indexing is, yeah, the subscript always denotes the agent that owns this interval. Right, so this is the definition of an allocation. What is an allocation? Nothing but a division of the cake, a partition of the cake, such that every, an n partition such that every agent gets a unique piece, gets a unique interval. So here's a picture. So say this is the first interval goes to agent 7, this is the second interval goes to agent 3, agent I gets some interval here, so on and so forth. So again, these are all pairwise disjoint and the union covers the whole thing. So you have divided the whole thing. That's an allocation. That's just the solutions that we are after. The output of a fair division exercise in the cake cutting context is such an allocation. So this is what we are after. This is what the protocols are supposed to produce as outputs. For the time being, yes. So the question was, like, are we ignoring the possibility of an agent getting 2 intervals or like getting 2 disconnected crumbs? For the time being, yes, but that's also a possibility where you can have you can divide it into many pieces. What's being assigned to an agent is again a union of these intervals. So now you'll not have n partitions, you'll have more than that, and again, but the disjointness sort of holds again. So you partition it in many, give collections of these intervals which are mutually pairwise disjoint, two different agents. We'll get to that, but for the time being, let's just, for simplicity, stick to this case. So, okay, finally, right, so after making you jump through hoops, here we go. What's the formal definition of fairness? At least in this context, I'll say that so again, this is, I am writing two definitions into one. The first definition is what does it mean to be proportional, or what does it mean to satisfy proportionality? What does it mean to be fair in this sense? It means that if I look at every agent, I look at the value that the agent I has for the interval that's been assigned to it. Again, recall the subscript convention. So Vi is the value of agent I, Ii is the interval that's assigned to I. This is at least 1 over n. Of course, I'm assuming here that the value has been normalized. So this is 1 over n times 1, the value that agent I has for the whole resource, and n again is the number of agents participating in the cake cutting exercise. So it just says that everyone gets at least a proportional share of the cake. Right. And the second definition, so this holds for all agents, of course. So is this square bracket n notation familiar to everyone? This means 1 through n, right? I have n agents, I have indexed them 1 through n, every agent satisfies this, so everyone is proportional, receives a share that's proportional. Second definition is of NV freeness, and we say that an allocation is NV free if and only if the value that agent I has for its own piece is okay. So what should I write here in this blank space? What goes here? What is that? Ij. Why is it Ij? So what, can someone remind me what NV freeness means? What is that? N minus, so okay, n is not a number, it's a indexing thing. So I mean, it's just like 1 through n here represents like identity. So it just means Abraham, Lot, you, me, Neeldhara, so on and so forth. So it says for every person. So if for example, if I look at I am I, my identity is I. So the value I have, like Vi, for the interval I receive in this allocation Ii is at least, first of all, the first thing notice is that it's Vi, the value I have for what? When will I be NV free? If Ij, right? J not equal to I. Why is this? Okay, if I write II here, why is it kind of? It's a good point. Why can I write II here? Exactly. I mean, okay, it's not greater than, it's equal to. I mean, I'll certainly not be envious of myself, right? I mean, I have that piece, I have that piece. It's sort of, there's no existential angst here. I look at my piece and, so okay, let me write it and then, so this is an important definition. If this is lost, then we are fighting an uphill battle. So let's sort of make sure this is appreciated. I is an index, it's an identity of an individual. So what this says that I look at every individual I. Now I looks at the value it has for the piece that's assigned to it. This is Vi of II, right? The value it's receiving under this allocation, under the allocation that I'm defining to be NV free. This thing right here, and this is said to be NV free if I looks at any other person, looks at you, and then says, okay, you have received Ij, but the value I have for my interval is at least as much as the value I have for your interval. So I'll not envy you, I'm satisfied with what I have. In other words, I'll not want to swap with you, right? Certainly, so it's envy free in that sense. It's a comparative notion of fairness. I am looking at every pair of agents and choose two of them, and now invoking this inequality for every pair. Note that when I instantiate for I, both the left hand side and the right hand side is Vi. Like I is doing this calculation in its own head. I says II is the value I have for myself. On the right hand side too, it's V of I, the value I have for Ij. I'm happy with what I have. So I do not envy anyone else, and this has to hold for every pair of, so it's a comparative notion in that sense. By contrast, the first definition, proportionality, is a threshold based notion, where you are saying, okay, I look at what I have, I look within, in the sense I just look at the piece, and the value I have for that piece is at least proportional, it's at least 1 over n the value I have for the total resource, right? So that's a threshold based notion of fairness, it's a comparative notion. Think back on the cut and choose thing for Abraham and Lot. We had sort of, we had both of these properties for the n equal to 2 case. I will not go through it again. It's a useful exercise for you to actually go back, look at the cut and choose protocol, work with the assumptions and the valuations we have outlined, and convince yourself of the fact that this property indeed holds for the n equal to 2 case for the case of 2 agents. And this is a good point for me to stop. We'll sort of see how easy and hard these sort of definitions are. But let me ask this question again. For general n, which one do you think is easier? Which one do you think is harder? Or they are kind of incomparable, always the same, don't care, looking late for coffee. Two implies one. That's perfectly right, yeah. Perfect. Exactly. So after the coffee break, we'll see why, with the 3 assumptions that we have made on the valuations, why 2 implies 1, why 2 in that sense is a stronger notion of fairness than 1. And like hopefully by the end of the day, you'll appreciate that 2 is really elusive. And in contrast, 1 can be achieved sort of, is a much more palatable, it's a computationally much more tractable solution concept. It's a notion of fairness that can be achieved much more generally. So that's sort of the agenda for the next lecture. But yeah, again, it's probably a good time to stop, and we'll sort of reconvene after the coffee break. All right, thank you.